text has been the primary form of documentation in human history. Today, large volumes of unstructured text data are being generated and disseminated at an unprecedented pace via such media as tweets, emails, and scholarly publications. The magnitude of these data has far exceeded our human capacity to read and digest. How can we possibly sift through the world of written text and access what we need? In what ways can computers, which have helped create this ever-growing pile of data, be harnessed to also help us discover relevance and meaning? Let's start with some basic issues and ideas for text processing. Imagine having a long legal document. It can be stored digitally along with other documents and files. In its raw text format, you can hardly use the document to compute and compare, unless we can convert the text into some numbers to be used in calculation. Indeed, the first step of text processing involves a general process called vectorization, which identifies elements in a text and assigns numbers or weights to them as its numerical representation. The result of this is a list of values, which can then be used for searching, ranking, and association. The very first step of vectorization is tokenization. Through tokenization, the text can be split into basic elements such as single words, phrases, sentences, or paragraphs. Taking single words as basic elements, look at the example here, John is quicker than Mary. The basic approach is the bag of words approach, which assumes as if the order of the text doesn't matter. And we are going to break this sentence into pieces of words where the order doesn't matter. So this will be split into words such as John quicker than Mary, which will become identical, ironically, to the sentence below, which is Mary is quicker than John. We know the meaning is different, but in the basic approach, in the bag of words approach, we are cutting the text into basic units, regardless of their order. So this is tokenization. In English, we can also apply some normalization techniques after the tokenization. For example, you can do case folding, which changes all tokens into lowercase. So John, lowercase, and capital John will all be converted to the lowercase John. You can also use something called stemming, which reduces tokens to their roots. So compression and compressed will be converted to compress. At some level, you can also try lemmatization, which converts words and different variants of the same word into their base form. So R and is will become B. Now, lemmatization does require a dictionary in that particular language, such as English here. Remember, these techniques are language and domain dependent. Aside from potential benefits of unifying tokens of the same type, token normalization may also lead to undesired consequences. For example, you may treat CAT, the company, and the word cat as the same, when they are actually about different things. So careful examination of data and application is necessary to determine whether related normalization techniques may be instrumental or detrimental. Also note that the tokens are not limited to single words. One can use a moving window to take 2, 3, or more consecutive words at a time to identify all possible are phrases or n-grams. Likewise, you can also use a moving window to identify any n consecutive characters as tokens. Character n-grams, for example, have shown its utility in applications such as spam detection, where junk emails may pad normal keywords with special characters to avoid being identified. Now let's talk about term weighting. Once tokens, single words, or phrases have been identified, they can be sorted and merged into a set of unique tokens, which we refer to as the dictionary. Suppose we have a book collection of the Chronicles of Narnia, for which we only store their titles. So let's use these titles as our small collection just for the case of demonstration. And with tokenization, we'll be able to identify single word tokens such as and, boy, down, horse, lion, witch, and so forth. Okay, and this creates a list of unique words which we regard as the dictionary. With the dictionary, we can then look at the occurrence of the words in each individual document and represent them using numbers. So the size of the dictionary here will increase with the size of the text collection and the length of each document. What is here is a binary representation where if a word appears in the document, the value is 1. If the word does not appear in the document, it is 0. So, for example, in document 1, the word lion does appear because document 1, if you remember, is the lion, the witch, and the wardrobe. So if the term boy does not appear in document 1, then the value is 0. So this is a very simple representation using bits 0 or 1. Imagine when, and there are more documents in there will be more 0 values in there. So a more efficient representation is called a sparse vector, where only non-zero values, ones, in the binary representation here will be stored. So document 3 in the matrix representation here can be represented as a vector of the columns where you have the value. So because document 3 has column 1, 2, 4, 5, and 7, where you have non-zero values, you can actually use 1, 2, 4, 5, 7 as the vector representation or the sparse vector representation for document 3. With longer documents, when full text is used for vectorization, it is useful also to consider term frequency, or TF. TF of DT is basically the number of times a term T appears in document D. So this is a simple count of times the number of times a term appears in the document. And we can simply use the term frequency as a term weight. So instead of using 0 and 1, we may use 3 or 100, depending on how many times a term appears in that particular document. So let's look at another example, 3 course titles as 3 documents. Okay, so the first course is information and systems, the second is data and information, and the third is system and system programming. Notice that the term system appears in the third document twice, and so its term frequency is 2. Other terms either appears in each document once or do not appear at all, so the other values are 0 or 1. A basic assumption of counting the occurrences in the term frequency way is that all occurrences are equal and should be counted equally. However, we would argue that the words are not created or used equally. Some words appear more frequently simply because of the effect of least effort. Some are stop words like and the that contribute very little in meaning. For many of these, there is one thing in common. They appear frequently not only in the current document but also in many other documents as well. So in general, we observe that some terms are used too broadly or too frequently in so many documents that they can hardly help us differentiate one document from another. They are too broad to be specific and informative. So stop words, for example, are too frequent to be useful. They are less informative. On the other hand, rare terms, which occur in fewer documents, tend to be more specific and more informative in these frequent terms. Okay, and so in this reasoning, we should assign more weight to the rare terms. Suppose you have a collection of documents called C, and N is the total number of documents in the collection. Imagine you randomly draw one document from the collection and try to calculate the chance that you will see a particular word, such as T. So lowercase nt is the number of documents containing term T. And so the probability of randomly drawing a document from the collection and seeing the term T, the probability should be nt divided by n, the number of documents containing the particular term that you want to see divided by the total number of documents in the collection. This is the chance that you will see that particular term. So back to the example of 3 course titles. We have 3 documents in the collection, so n is 3. We only have 3 documents, right? And so let's look at the term data. If you randomly draw a document from the 3 documents collection, how likely you are going to see the term data? Now, if we look at the collection, data only appears in one of the course titles, one document only. Okay, so the chance of seeing data in the random drawing is going to be 1 out of 3, because you are going to draw one document and there's only one document containing the term, and there are 3 documents totally in the collection. So it's 1 out of 3. Now let's look at another term, which is and. The term and, if you remember, appears in every single document in this small collection. So out of the 3 documents, all 3 documents contain the term and. So the chance of seeing and in a randomly drawn document is 3 out of 3, which is 100%. So this is the probability to see each term. Now, here is the concept of this notion of inverse document frequency. Earlier we reasoned that the more frequent a term appears in more documents, it should be less useful and should be given a lower weight. When a term is rare and appears in fewer documents, it should be given a higher weight. So here is the inverse relation between the number of documents a term appears in versus how informative the term is. And because the relation is inverse, if we want to have a weight for each term, we should look at the inverse document frequency. And it turns out that the inverse document frequency is in fact the amount of information that you gain from seeing the term in the document, which is the logarithm of the probability value inversed. The IDF, or inverse document frequency, is log n divided by nt. And if you remember, nt divided by n is the probability that you will see the term. Okay, so this is the logarithm of the inverse probability, which is called inverse document frequency, or IDF. So the TF, the term frequency, is the document-specific statistic for each term. IDF, on the other hand, is a collection-wide statistic for each term in the whole collection, regardless of which document it appears in. So they address two separate aspects of term weighting and are often combined for document representation. And the combined weighting scheme, namely the classic TF-IDF, assign a term weight by multiplying TF and IDF. So the weight of dt, which is the weight of term t in document D, is a TF, the term frequency of the term t in document, how many times the term appears in document, times the log n divided by nt, which is IDF. So let's look at the example again to see how we can use TF-IDF to represent the documents. Remember, we have this term frequency representation of the documents. Document 1, n appears once, information appears once, system appears once. For document 3, term n appears once, program appears once, and system appears twice in that document 3. Now we can compute the IDF as well based on the probabilities. Remember, for data, it appears only in one document, so the probability of seeing the term data is 1 out of 3. The IDF is the inverse, the logarithm of the inverse probability, so it's log 3 divided by 1, and it becomes about 0.48. Okay, now let's look at another extreme example, the term n. Term n appears in all 3 documents, so the probability is 3 divided by 3, which is 100%. Okay, you take the inverse of 1 is still 1, and log 1 becomes 0. This means that the term n appears so frequently, it appears in all the documents, that it becomes useless, and the weight has been reduced to 0. Now we combine the TF and IDF together in this new representation. Let's look at term n in document 1. So n appears in document 1 for 1 time, so the TF, term frequency, is 1. The IDF, as we just calculated, is 0 because n appears in all 3 documents. So the probability is 1. We take the reverse of 1, is still 1. We take the logarithm of 1, becomes 0. So 1 times 0. So n, the weights associated with n will be reduced to 0. Let's look at another example. The system appears twice in document 3. And if we go back to the previous slide, the IDF weight for system is 0.18. So 2 times 0.18 is 0.36. So this becomes the TF-IDF representation.